Okay, welcome back. In this video, we're going to be talking about our first hypothesis tests, specifically one sample z-tests and one sample t-tests, kind of lumping the conceptual and practical piece together here. So, I've shown you this visual before. This is a full decision tree of all the hypothesis tests that we'll be going over in this course. But this is a lot to take in, so don't worry. We'll start it simple with these two at the top here. And so we haven't defined factor yet. We'll be doing that here in the next couple of modules. The base we can think of, here we're looking at one independent variable, one group, and the key difference between these two tests is whether or not we know the population variance. If we do, we're going to do a z. If not, we'll do a t-test. And so this is something that we talked about when we talked about estimation and confidence intervals. And so the only real piece this slide is adding here is to show that with z-scores, again, since we know the population variance, we can use standard error. But with t-scores, we have to use estimated standard error. And we'll kind of walk through that. Before we get into the specifics of each test, I like to step back and remind us of the steps to hypothesis testing that we've seen before. And specifically, I want to focus on the first step and our discussion about null and alternative hypotheses, because we'll need this to demonstrate and learn something new. And so, for example, we looked over this slide previously. I'm not going to spend time on the actual hypotheses themselves, but I do want to focus on the actual notation here, right? And so in the first example, we had a null hypothesis in which, or basically what we were doing in this hypothesis test was checking for any difference between the alternative and null hypothesis, right? Looking for any alternative to the null. So we call that a non-directional two-tailed test. And so this graphic over here is a little bit backwards, and that's what's the top on the right is the bottom on the left. But and H sub A here, it's what we essentially mean for H sub 1, right? H, the alternate hypothesis. And so in a two-tailed test, we're saying the population mean is not equal to something, right? That's our alternative hypothesis. And so we don't care which direction the distribution shifts. We're just interested in any shift, right? And that's why we have two tails. With a directional or one-tailed test, we expect it to shift one of two directions, right? We expect the mean to be greater than the population mean or less than the population mean, right? And so you can see here that that's what distinguishes the left and the right-tailed test. And so we'll go through, I guess, a little bit more precise example in a sec. But to elucidate the difference a bit more clearly, like I said, with a non-directional two-tailed test, we're testing this kind of hypothesis, a not equal to, and we're interested in any alternative form, or sorry, any alternative from the null hypothesis, regardless of which direction it's going. With directional, we have a specific alternative in mind, right? And so more precise terms, an upper tail critical test, if we expect H sub 1 to be greater than H sub 0, then we'll place the level of significance in the upper tail of the distribution, or in other words, on the right side. And then lower tail critical, it's just the opposite. We'll place the level of significance, or the rejection region, in the lower tail, or the left side. And so to put those all in one slide here, so again, non-directional, we have these two tails. And since we have two tails, if we're doing a p of 0.05, or say we set our alpha, our decision criteria, say we set our alpha at 0.05. Well, then in order to get p, right, or the probability within each rejection region, we need to take that alpha divided by 2 to account for the fact that we have two tails that is being distributed over. And so in other words, here we'll have 2.5%. If our p is 0.05, we'll have 2.5% in this region and 2.5% in this region. And these visualizations are specifically for a z distribution. And so you can see that alpha of 0.05 and the z distribution corresponds with z plus or minus 1.96. And now for a directional upper tail critical, well, in directional or one tail tests, p equals alpha, right? Because now we're taking that entire criteria or that entire proportion and putting it in one tail of the distribution. So here to get a p of 0.05 or an area of 5%, we're at a z of 1.645, right? So you can see that's a lower z-score than the non-directional. And then lower tail is the exact same, just the opposite, right? So P is still alpha. It's just that now we have minus 1.645 instead of positive 1.645, right? So some key distinction here and something not to overlook or to be careful not to overlook is when we're looking at alpha and determining P in two-tailed tests, we need to divide alpha by 2 to distribute that across the two tails. Okay, so let's get into the tests here. So first, for a one sample z-test. So again, here we know population variance. And so, yeah, we're testing hypotheses about a population mean with some known variance. Our general formula for this, I forget if I've shown you this before. So I apologize if I'm repeating myself, but z obtained equals m minus mu divided by the standard error of the mean. Right, and here m represents our sample mean, mu represents population mean. And to calculate standard error, we have variance divided by sample size, the square root of variance divided by sample size, or standard deviation divided by the square root of the sample size. Right, and so let's start with one example of a non-directional or a two-tailed one sample z-test. And so these will look familiar because when we did estimation and confidence intervals, these were essentially the same examples, just slightly different prompts, because then I was asking you to estimate values. Now I'm asking you to test hypotheses. But I do encourage you to go back and compare the two. So in this one, IQ scores in the general healthy population are approximately normally distributed at 100 plus or minus 15. And so let's say we collected a sample of 100 students and we found a mean IQ score of 103. So that is 3 points higher than the population mean. And so what we want to do is to compute a one sample z-test for whether or not we will obtain the null at a 0.05 level of significance. In other words, is our sample mean of 103, is that far enough away from the population mean to suggest that we should reject the null hypothesis that the population mean is actually 100, right? And so I'm getting ahead of myself, so let's back up here. So let's walk through these steps one by one. First one, stating the null and alternative hypotheses. Well, the null hypothesis, as I just stated, right, is what we already know, or what we presume to be true, which is that mu here equals 100. Mean IQ scores are equal to 100 in the population. And the alternative hypothesis then is simply that mu is not equal to 100, or mean IQ scores are not equal to 100 in the population. And again, in this example, we know that our sample score is higher than the population mean, or our sample mean is higher than the population mean. But for the sake of this example, we're considering this a two-tailed test, right? Just looking at our value and seeing if it's different. Okay, so we've stated the hypotheses. Now let's set the criteria. Okay, well, what is alpha? 0.05, right, as demonstrated below, 0.05 level of significance. And you'll recall that in, like we just talked about, in non-directional tests, p equals alpha over 2. So in order to identify our p-values, we need to take that divided by 2, which will be 0.025 in each tail. All right, and so then we'll look these up in our unit normal table. And once again, so we're looking for column C, right? We're looking for 0.025 in column C, right? Whatever this region will be. And you'll find plus or minus 1.96, right? As I just showed on the earlier slide with the table, right? And so that is our critical value of Z, right? Plus or minus 1.96. And I've used this term already, so I guess to more explicitly define it. These regions beyond the critical values, the ones shaded in blue on this slide, those are called the rejection regions, right? So in other words, this is our critical Z value. If we calculate our Z obtained, or our obtained Z score, if we calculate Z obtained and it falls in one of those rejection regions, then you guessed it, that means we're going to reject the null, right? That's why they're called rejection regions. And so now let's compute the test statistic. Once again, here's our formula. And so we'll just plug in our values. First, we need to calculate standard error, the denominator over here, which is standard deviation divided by the square root of the sample size. And so here we have population, or yeah, again, since we're doing a z-score, we know about the population variance, and since we know about it's not explicitly reported here, but population variance, again, just being the standard deviation squared, right? So here the population standard deviation is 15. The sample size was 100. I didn't explicitly write it, but n equals 100 based off the description. So this is going to be 15 divided by 10, 1.5. And so now we have our denominator for our z formula. And we'll plug that in, our sample mean, our population mean, and the standard error, and we get a z obtained of 2. So now let's make a decision with that. So we need to compare our obtained value, that 2, to our critical value, which was plus or minus 1.96. And so to put this on a graph here, I just blew up the image you saw previously. So this is our critical region. And if we overlay it, right, we find that our z obtained is 2. Right, let me do that a little bit more quickly. So you can see they're real close, right? Because it's 1.96 and 2, so it's only 0.04 standard deviations apart. But nonetheless, that is greater than a critical value and does fall in the rejection region. So therefore, our decision is to reject the null hypothesis. And the reason it's in this upper tail is intuitively because our mean in our sample was higher than the population mean, right? And so we decide to reject the null hypothesis. Here's a image from the textbook, if this is a little bit more, I guess, clean to interpret than my jumbled overlapping images on the other slide. But again, showing the same thing, that if we had to obtain z-score in this region, we would retain it, but we have one in the rejection region, therefore we reject the null hypothesis. And so if it helps to interpret this, to basically start here and work backwards to explain what we just found. Well, so we obtained a z-score of 2, right? And if I wanted to, I could go back and look in the unit normal table and find the p-value for that z-score, and I would find a p of 0.0228. And again, if we plug this into the formula, if we know that p is alpha over 2 in this non-directional two-tailed test, then I can do some algebra here and find that the p-value is 0.0456 for this overall test. And so in other words, the overall test for this hypothesis, the p-value is less than 0.05, therefore we reject the null hypothesis. All right, so it's just another way to go in reverse to identify the specific p-value for our test and to demonstrate again why we are rejecting the null. And so the overall conclusion here is that the mean scores on IQ tests in this population is 103, not the value stated in the null. Right, so in other words, we're essentially stating that the population mean must be wrong. Right, so either the population mean is wrong or this population is fundamentally different in some way. And so again, that also kind of goes to show the limitations of hypothesis testing, in that we're getting information, but we're still talking about these distributions, and the direct relationship between these distributions and what they mean practically speaking is still up to some amount of interpretation. That's why it's very important to apply these with knowledge of psychological theory and all, or whatever theories you might have as a social scientist in your respective fields. And so this plot here, I made this in Jamovi to give you a little bit, I guess a slightly different perspective. So here, this is, again, just going to show that when we're doing these statistics, we're talking about these distributions of sample means, and we're doing all these, or there's a lot happening behind the scenes, right? And so you can see the population mean and standard deviation, 115. So that's the population of IQ test takers, essentially. And then our little sample, or our little distribution of sample means is right here with a standard error of 1.5. And so you can see our sample mean falls over here in this critical region for that distribution of sample means, right? And so that's just another way of depicting that our results showed that we should reject the null, because it seems like there is something different about the sample mean we collected. Therefore, it seems like there's something about our population that that is incorrect or invalid in this context. Okay, so that's a non-directional. Let's do a directional test now. And specifically, let's do an upper tail critical test. Okay, so for this one, population mean reading proficiency in elementary children or yeah, I'll back up. Let's say we have a bunch of elementary kids, so like grade schoolers, like fourth grade, third grade, that kind of age group in general. And we put them in a reading program, and we assess their reading proficiency before and after the program. And we find that the population mean, or the average increase in reading proficiency, is 12 points. What those points mean, I don't really know. We're not going to worry about it here. But let's say that the population mean, on average, they increase 12 plus or minus 4 points. And so this specific year, we select a sample of 25 students who are in the reading program, and we find that their overall average improvement is 14 points, right? So that's our sample mean. And now I want to compute a z-test to see if this is significantly different, right? If this increase in our mean is a significantly or statistically significant increase from the population mean. And so here, now we're worried about a specific direction. We're doing an upward tail critical test. So we'll follow the same steps, starting with step 1. What is our null hypothesis? Well, here we're going to say that the population mean is less than or equal to 12. So in other words, with the reading program, mean improvement is at most 12 points, right? So in this case, with directional hypotheses, we're basically taking that population parameter, and in this case, we're saying that that's the most it can be. And then our alternative hypothesis is that it's higher, right? Or it's trending towards the upper tail. And so, in other words, with the reading program, mean improvement is greater than 12 points in the general population, right? So we're stating that the population mean is actually higher, right? That's the alternative hypothesis. And so let's set our criteria. Again, alpha equal 0.05, because that's the general procedures that we follow, and it's what was provided to us here. And so now let's look up the values in the uninormal table. And if we do that, we'll find that this one falls in between two z-scores, between 1.64 and 1.65. And so if that ever happens, just take an average of the two. So 1.64 plus 1.65 divided by 2, and we'll get 1.645. So that is our critical value and cutoff for the rejection region. So that's what this looks like then on an actual distribution, right? So we can see here an area of 5% corresponding to p of 0.05. Okay, compute the statistic. Well, here, once again, we need to calculate standard error first. And if we do that, plug in our standard deviation, our sample size, we get a standard error of 0.8. And then we'll substitute those into the formula and compute a z, and we'll get an obtained z-score of 2.50. And now we just need to compare the two, right? So once again, our critical z was plus or no, sorry, that should just be 1.645, not plus or minus. I apologize for that. Then our z obtained was 2.5. And so you can see if you go down here, right, you can clearly see that our z-score falls, or our obtained z value falls in the rejection region. So it's greater than the critical value, does fall in the rejection region. Specifically, the p-value is 0.0062. And so we decided to reject the null hypothesis. Once again, a plot from Jamovi if you'd like to see this, with the population distribution and our distribution of sample means here. And I guess one key thing to note here too is that you'll see that the sample mean here falls at essentially a proportionally same place, because this here is just a blown up version of this little distribution down here, right? With some slight changes, but essentially that's what it is. If you're not familiar with why that's the case or what I mean by that, then I encourage you to go back and watch previous videos. We won't spend time on it here. Okay, so let's talk about effect size now. This is something that we also mentioned in, I guess, just in the previous video for this module. But so we've talked about Cohen's d already. Let's determine that for the example that we just did. And you'll recall the formula for Cohen's d. Very similar to the formula for our z-score, with some slight difference in what's in our denominator, essentially. And so if we do this, we plug in our values and get a d of 0.5. And so I encourage you to stop the video at this point and go back to your previous notes to try to identify what that means. And whether or not you've done that, I'll proceed. To answer my my question there, a D of 0.5 means that the observed effect shifted 0.5 standard deviations above the mean of the population. And so in other words, the distribution looks like this, right? Or that's roughly what a Cohen's D of 0.5 looks like. And so in other words, students in the reading program scored 0.5 standard deviations higher on average than students in the general population, right? So that's essentially summarizing what we found in this study using that one statistic, Cohen's D. And that representing then the overall distributions and how much they overlap. Okay, so now let's move on to t-tests. I might move a bit quicker here because t-tests and z-tests, to me, they feel very similar, just with slight differences. And that, well, for starters, we don't know the population variance, right? That's the key difference between a z and a t. And so once again, if we don't know population variance, but we do know sample variance, which we pretty much always do, we can calculate t instead of calculating z. And once again, just to refresh from what we talked about when we talked about estimation, t-tests use estimated standard error, or in other words, an estimate of the standard deviation of a sampling distribution. And so this is our formula here. Again, almost identical to a z formula, except the denominator changes from standard error to estimated standard error. And here we're testing means about a population with unknown variance. And the t-distribution, though, it's a little bit weird, and that you can see on this graph, the solid blue line is a normal distribution. T-distributions change their shape depending on the degrees of freedom. If you're not sure what that term means, we'll define it here in just a minute. But you can see as the degrees of freedom decreases, our tails actually come up off the x-axis. And the reason for that is that the t-statistic varies more than the z-statistic. The z-statistic is distributed just as a normal distribution. The t-distribution is not. It depends on the degrees of freedom. And the reason for that is because we're using an estimate to calculate t rather than the actual value of the variance, right? And so in other words, because we're estimating variance in our calculation of t, the t-statistic will therefore be more likely to vary. However, as our degrees of freedom increase, then we will see that our distribution becomes closer to a normal distribution. And I'll show a visualization in a sec to explain that a bit more. I already said that. Yeah, we don't need to spend time on this. 3 assumptions. I'm not going to worry about those. If you have questions, we can talk about them, but I'd rather get to the juicy parts. So when we are calculating t-statistics or computing t-tests, we're going to look at a new table in the textbook. And so we use this t-table backing up, we use a t-table just like we would use a z-table, right? We're locating probabilities and critical values. The key difference here is that now we have proportional one-tail and proportionate two-tails combined, just reflecting the fact that we might use this for one-tail tests or two-tail tests, right? For directional or non-directional. And in order to use this, we need to know a few things. First, location of rejection region, one tail or both tails. Alpha, so what is our criteria, right? So for example, if our alpha is 0.05 in one tail, that would be this column. If it's 0.05 in two tails, that would be this column, right? So that will determine where we look. And we also need to know degrees of freedom, right? This column on the left. And we can get degrees of freedom by knowing n, our sample size. And I'd like to take a quick tangent to explain what these are. And I'm going to tell you a story, right? So bear with me, don't fast forward. Or I guess fast forward. Don't skip this part. If you're fast forwarding this, then I don't know what kind of system you're using. So degrees of freedom. These are the number of degrees of freedom. That represents the number of values that are free to vary in the final calculation of a statistic. That probably doesn't feel intuitive at all. So let's explain this with a story. A story that, if you're here in Alaska, might be close to your heart. So let's say that I'm going ice fishing for a week, right? And yeah, taking a week off. I'm actually recording this in March currently. Whenever you're listening to this, it's March for me right now. And so winter is still here, but it's definitely starting to fade. Spring is on the way. And so I'm going to go ice fishing for a week to get in, just one last little bit of winter. And let's say I make a bet with somebody of mine and I say, you know what, I bet I'm going to average 2 fish per day on this trip, right? I'm a great ice fisherman. Um, there's really not that much skill involved once you start. But I'm going to catch 2 per day, and let's say I put some money on it, so it's really important to me. And so what I want to know is, or to explain degrees of freedom in this example, and how many days can my yield vary freely in pursuit of this goal? That probably feels weird. So, in other words, how many days can I wake up in the morning and not have a specific number of fish that I have to catch that day in order to get an overall average of 2 per day? Right? In other words, how stressed out am I going to be over the course of this trip? And how many days am I going to wake up and say, oh shit, if I'm going to average 2 per day, then I have to catch X number of fish today? Let's go ahead and find out. And so, yeah, so remember this, the goal is 2 fish per day. And so let's say I wake up on day one, and I'm not actually writing this table out, but I'm thinking about it, and I'm like, all right, I need to get 2 per day. So what do I need to do here? I'm like, okay, well, it could vary a lot, right? Like I could get 2 per day if I get like 1 today, 3 tomorrow, so on and so forth, right? This is just one example on this table of how I could average 2 fish per day with a lot of variety in how many I'm catching each day. Maybe I'm just some, excuse me, some weird fish catching robot, and I can catch exactly 2 per day. That would be one way to average it out. But that's probably not realistic. And hell, even if I have a bad day today and I don't catch any fish, there's still plenty of room for it, right? I can still vary a lot, and I can have days when I catch no fish, right? So day one, I'm just like, whatever, I'm gonna be fine, right? All the days at this point can still freely vary, right? And so I start that day. Let's say I catch 2 fish, right? I'm like, great, my average is currently 2 fish per day. I'm crushing it. Next day, I catch 3 fish, and I say, you know what? My buddy's gonna owe me so much money because now I'm averaging 2.5 fish a day, right? I've got 5 fish so far. But then the third day, my progress comes to a grinding halt. I catch no fish, and I say, oh shit. I do some napkin math, and I'm like, okay, now I'm averaging less than 2 fish per day. So I'm starting to think about it. I'm like, okay, what do I need to do now in order to average out to 2? How can this look, right? How much freedom do I have, and how many fish I'm catching? And I might say, okay, well, if I catch 1 tomorrow, 2 the next day, right? And I start doing some math, like, okay, like this is still totally reasonable based off what's happened so far. This could just be a bad day. Even if I have a couple of bad days where I only catch 1 fish tomorrow, 1 fish the next day, and then I finish strong, I can still average out to 2, right? So at this point, it seems like the 4 remaining days can still freely vary, right? Like it seems like, yeah, there's still plenty of freedom. And so let's say I fish that day and I catch 1, and I'm like, okay, that's good. I'm glad I caught 1, but my average is still dropping. That's not good. The next day I catch 2, and I say, okay, this is good. That's more, right? But my average is still low. If I'm going to get to 2 per day, then what do I need to do here? I'm probably going to need to show up and compensate for my poor performance the past few days. So let's see. If I catch 3 per day on the next 2 days, then I'll average 2 per day. If I catch 4 tomorrow, 2 the next day, and then I wrap it all up, then I'll have 14 fish. It's an average of 2 per day. Hell, I could have one more really bad day, but then I'd have to finish really strong, right? So you can see I'm starting to feel a little bit of stress and pressure. But at this point, the 2 remaining days can still freely vary, right? Like it doesn't matter, right? Or it matters, but there's still flexibility, right? There's still wiggle room. But then, dud, I catch no fish, right? Then I'm like, oh shit. Okay, I have one more day. If I'm gonna win this bet, how many fish can I catch? Right? And the answer is that I have to catch 6 at this point in order to hit my average. And so now the 1 remaining day cannot freely vary, right? And so that is what we're talking about when we talk about degrees of freedom, right? Is how many things are free to vary when we're computing some sort of statistic. At this point, 6 of those days could vary, but then on the 7th day, it's a done deal, right? If I'm going to hit the average, it has to be this number. It is no longer free to vary. And so to explain that and kind of summarize that, I can wake up on 6 days without having a specific number of fish that I have to catch to meet my goal. Right, and 6 of those days I could wake up and say, you know what, whatever I catch today, I can still meet my goal. But then on the 7th day, I wouldn't be able to. Right, so another way to describe this is that there were 6 days with yields that were free to vary in order to meet my goal of 2 fish per day on average. Or in other words, there were 6 values that were, or wait, okay, this is slightly different. There were 6 values that were free to vary in order to calculate an average of 2 fish per day. Or in other words, there were 6 degrees of freedom in the final calculation of the statistic. Right, that is what we mean by degrees of freedom. And so in this example, degrees of freedom was 7 days minus 1 day equals 6 days, right? So 6 of those days were completely free to vary. And that is why our formula for degrees of freedom is typically n minus 1, right? N is our sample size minus 1, just using days of the week as an example with our sample, or as our sample size. All right, so I hope this helps to explain and conceptualize what we mean by this, because this is one of those things no one really explained to me well ever, actually. And so this is an example that I came up with, and I hope does a better job of explaining it than I ever heard when I was a student. So going back to this, degrees of freedom, in a t-distribution, dft equals the degrees of freedom of the sample variance. Or yeah, you can see here dft equals n minus 1. And so as our sample size increases, some things happen. For starters, our sample variance more closely resembles the population variance. And you'll recall the population variance is what we don't know in a t-test. That's why we're doing it in the first place. If we knew that, we could just do a z-test. So in other words, as the sample size increases, our sample variance is getting more and more similar to or analogous to the population variance. So our accuracy is getting a little bit better, you could say. And so as we're doing this, our degrees of freedom increases along with our sample size more closely resembling the population variance, or sample variance, sorry, more closely resembling it. And as our degrees of freedom increases, the shape of the t-distribution changes. And so just like you saw on the previous, or on a previous slide, the tails approach the x-axis and the probability of outcomes in the tails becomes less likely. And so let's look at a quick visualization that will explain this. This is coming from our psychologist. Oh, this is the wrong one. Let me go back here. Okay, t-distribution. There's a lot to take in on this. Let's not worry about all these extra plots. Let's just focus on what this shape looks like. And so you can see here this dotted line represents the normal distribution. And this blue line, the blue solid line, represents the t-distribution. So you can see at degrees of freedom of 1, the tails are much higher than the normal distribution. In other words, there's a higher likelihood of obtaining a statistic in these rejection regions. And then as our degrees of freedom increases, like let's go to 5 to start. Right, even at that point, you're starting to see this t-distribution more closely mirror a normal distribution, to the point where if we get to like 35, right, it's getting very, very close. Then all the way up to 100, and it's essentially identical, right? And so let's go back here to show like more gradual change. 1 to 2, 2 to 3, right? And so as we do this, you can see those tails are coming down and approaching the x-axis. Therefore, the probability of a value in these rejection regions is lower. Okay, let's go back to this, right? So yeah, so that's essentially what's happening in the t-distribution here. So hopefully that visualization helps to explain that a little bit, and I'll make sure to post that link for you in Canvas. So as to an example, this should feel very familiar to a z-test, but nonetheless worth going over. So we've talked about this one in the past. So let's say these people studied relatives of patients with OCD. Their sample size was 18, and they measured social functioning using this 36-item inventory, and basically the scores of health or social functioning, whatever you want to call it. They range from 0 to 100, 0 being the worst, 100 being the best. And the overall population mean on this score, or on this inventory rather, is 77.43. And in this sample of relatives of patients with OCD, the mean was 62 and the standard deviation was 20.94. And so essentially what I want to do here is to test whether our sample mean significantly differs from the population mean at an alpha of 0.05. So we'll follow our steps as per usual. Step 1, our null hypothesis is that mu equals 77.43. And our alternative hypothesis is that mu is not equal to 77.43, right? So I forget if I mentioned previously, right? This is a non-directional test, obviously. Yeah, just basically stating, is there a difference between our sample mean and the population mean? So setting our criteria in step 2, we already have our alpha. We have our degrees of freedom. And this is a two-tailed test. However, I will note, in this case, when we're looking for our p, since the t-table already accounts for 1 and 2 tails, we don't need to divide our alpha by 2 like we did for z-scores. That was simply because of the way the table is set up. The t-table, it already accommodates this. So we just need to look up p equal 0.05 and proportion of 2 tails combined at a df of 17. I don't think I have an actual picture of that up here. So let me know if you have any trouble with that. But what we'll find is t plus or minus 2.110. And it's plus or minus because it's two-tailed. So to show that in a graph here, that's what we see. Right, this is now a t distribution, t minus 2.11 and plus 2.11, right, splitting out the alpha or the p into 2.5% on either side of the distribution. And so in other words, as another image from your textbook, if we get a value that falls in these rejection regions, then our decision is to reject the null. All right, same as for a z-test. So let's compute the t statistic. Following this formula, first estimated standard error, plug in our values, do the same thing with t, and we'll get a t obtained of minus 3.126. Make a decision. Okay, let's compare the two. Here was our previous values, our critical values. Our t obtained is all the way down here. All right, I'll go back and forth a little bit to show you that. Therefore, we're going to handily reject the null hypothesis. P is less than 0.05 because our t obtained does fall in the rejection region. Right, another way of depicting that right here. And so in other words, we could say that according to this hypothesis test, social functioning scores among relatives who care for patients with OCD were significantly lower than scores in the general healthy population. And that's how we report all of our statistics. Okay, so effect size, let's calculate this real quick. I'm not going to spend time on it, but basically it's the same formula, except now we're doing standard deviation, or sample standard deviation instead of population standard deviation. If we do that, we get a value of minus 0.74. It means that the effect shifted 0.74 standard deviations below the population mean. So in other words, relatives caring for OCD patients had reduced social functioning scores that were, on average, 0.74 standard deviations lower than people in the general population. These values aren't true to scale, but the overall image is. And so that's roughly what a D of 0.74 looks like in this example. Okay, and so real quick before we wrap this up, I want to mention that there are other measures of effect size. Cohen's D, right, like we just showed on the other slide, Cohen's D is measuring effect size in terms of standard deviations. Other statistics of effect size will measure it in terms of the proportion of variance. What is that? Well, that's the percent of variability in a dependent variable that can be explained by or accounted for by some sort of treatment. In other words, variability explained over total variability, right? That's proportion of variance. Yeah, so in other words, how much things, back up. So if we have some specific variable and it varied, right? The total variability is all the ways that it varied. Variability explained is variance that could be attributed to or explained by something specific, something else. And here we call it a treatment. That's kind of a clinical term. You can kind of think of it as another variable, right? So it could be any characteristic, way we treat a sample. It probably depend a lot on the research design. But here, the key thing is to know that when we talk about proportion of variance, it's how much variance in a dV that can be explained by something else. Two basic ways to measure this are eta-squared and omega-squared. Very similar, it's just one is more conservative than the other. Eta-squared tends to overestimate, so omega-squared is more conservative, and that leans towards underestimating rather than overestimating, which is probably ideal. Yeah, so you can see here, formula is very similar, just slightly different in their computation. And so real quick as an example, let's do eta-squared for the example we just did. All we have to do is plug in our t and our df into this equation. And if we do that, we get 0.36, which means that 36% of the variability in social functioning can be explained by the fact that participants were relatives who care for patients with OCD, right? That treatment in this study, right? And so that's when we talk about proportions or variance explained, this is what we're referring to. And so this table walks through the measures of effect size and how to interpret them. Basically just a resource for you to have if you'd like one. But this video has been plenty long, so now let's stop. Thanks for tuning in.